I am Dr. A. Nilima, Assistant Professor of Mathematics at MVSR Engineering College. Today, we are going to learn about higher order differential equations. It is the title of Unit 3, Mathematics 2. Today, we are learning Part 7 of this unit. In this presentation, we will be learning about an equation which is reducible to linear differential equation with constant coefficients. Specifically, we will be learning about Euler Cauchy's equation. The other name for Euler Cauchy's equation is Cauchy's homogeneous equation. Let us see what Cauchy's homogeneous equation is or Euler Cauchy equation is. An equation of the form x power n into dny by dx power n plus a1 into x power n minus 1 into dn minus 1y by dx power n minus 1 plus a2 into x power n minus 2 into dn minus 2y by dx power n minus 2 plus and so on plus a n minus 1 into x into dy by dx plus a n into y is equal to capital X, where ai's are constants and capital X is a function of x, is called Cauchy's homogeneous linear equation or Euler Cauchy's equation. Now if you observe this equation carefully, we observe that it is a linear differential equation because degree of the dependent variable and its derivatives is 1, and it doesn't contain any products of dependent variable and its derivatives or products of various order derivatives in this equation. So it is a linear differential equation, and moreover we are having RHS as a function of x, so it is a non-homogeneous linear differential equation with constant coefficients. So it is a non-homogeneous linear differential equation, and if we observe the coefficients, it is not a constant coefficient equation because coefficient of the derivatives of the dependent variable are not constants. Therefore, it is not constant coefficient equation. It is a variable coefficient equation. Here coefficients are functions of x. Therefore, we can call it as a variable coefficient equations. They are not constants, so it is a variable coefficient equation. Specifically, it should take this form x power n into dny by dx power n plus a1 into x power n minus 1 into dn minus 1y by dx power n minus 1 plus a2 into x power n minus 2 into dn minus 2 y by dx power n minus 2 plus and so on plus an minus 1 into x into dy by dx plus any is equal to capital X. An equation of this form is called Cauchy's homogeneous equation or Euler Cauchy equation. Here homogeneous linear equation doesn't mean here RHS is 0. It is Cauchy's homogeneous equation. By the definition, it is a non-homogeneous equation, but we call this non-homogeneous equation as Cauchy's homogeneous linear equation. Some homogeneity is there here, that is x power n here and nth derivative here, and x power n minus 1 here and n minus 1th derivative, x power n minus 2 here and n minus second derivative, like that x into first derivative, x power 0 into 0th derivative. Some homogeneity is there, though the equation is non-homogeneous. Specifically, this equation is also called as Cauchy's homogeneous linear equation or Euler Cauchy equation. Now let us learn the procedure to solve Euler Cauchy equation. So your first step is to write the given differential equation in this form, that is x power n into dny by dx power n plus a1 into x power n minus 1 into step 1. Write the given differential equation in the form x power n into dny by dx power n plus a1 into x power n minus 1 into dn minus 1 y by dx power n minus 1 plus a2 into x power n minus 2 into dn minus 2 y by dx power n minus 2 plus and so on plus an minus 1 into x into dy by dx plus any is equal to capital X. So your first step is to compare your given differential equation with this equation. If it takes this form, then we can call it as Euler's Cauchy equation. Now coming to step 2. Once you have identified that the equation is Euler Cauchy equation, put x is equal to e power z. X equal to e power z means z will be log x to base e. So with this substitution, this equation will be reduced to a linear differential equation with constant coefficients. Let us see how it reduces. Dy by dx will be equal to dy by dz into dz by dx by chain rule. So this is equal to dy by dz into what is dz by dx? Z is log x. So dz by dx will be 1 by x. Derivative of log x is 1 by x. Or this can be written as x into this x when taken to the LHS, this becomes x into dy by dx is equal to dy by dz. Now denoting d by dz with capital D, this x into dy by dx will be equal to dy by dz. In a similar manner, when you go for d square y by dx square, this can be written as d by dx of dy by dx. What is dy by dx? Dy by dx is 1 by x into dy by dz. So double derivative of y with respect to x is nothing but d by dx of 1 by x into dy by dx. Now if you observe this carefully, here d by dx of this is a function of x, and basically y is a dependent variable, y is a function of x. And what is the z here? Z is also a function of x. So here dy by dz is also a function of x. So you can differentiate 1 by x into dy by dz with respect to x. For this you need to apply product rule. So that is d by dx of uv is equal to u into dv plus v into du. So treating one of the function as u and the other one as v, this will be equal to derivative of first function, that is minus 1 by x square into dy by dz plus 1 by x into derivative of the second function with respect to x. So it will be d square y by dz square into dz by dx. Again we are applying only chain rule here. D by dx of dy by dz will be d by dx of dy by dz can be written as d by dz of dy by dz into dz by dx. So d by dz of dy by dz will be d square y by dz square into dz by dx. So we have applied product rule here and chain rule for evaluating d square y by dx square. So this will be equal to 1 by x square into dy by dz plus 1 by x into d square y by dz square, and here this dz by dx is 1 by x. So this will be simplified as minus 1 by x square into dy by dz plus 1 by x square into d square y by dz square. So take 1 by x square common from these two terms and cross multiply. You will get x square into d square y by dx square is equal to d square y by dz square minus dy by dz. So this is equal to, if we denote d by dz with capital D, this term will become d capital dy and this term will become capital D square y. So x square into d square y by dx square will be equal to d square y minus dy, which is equal to d into d minus 1 operated on y. In a similar manner, we can derive x cube into d cube y by dx cube is equal to d into d minus 1 into d minus 2 operated on y, and so on. Like this you can derive all the terms of Cauchy's homogeneous equation. So this is step 2. In step 2, we need to substitute x is equal to e power z or z is equal to log x to base e, and then treating capital D is equal to d by dz, we need to write x into dy by dx is equal to capital dy x square into d square y by dx square as d into d minus y operated on y, and x cube into d cube y by dx cube as d into d minus 1 into d minus 2 operated on y. Similarly, x power 4 into d power 4 y by dx power 4 can be written as d into d minus 1 into d minus 2 into d minus 3 operated on y, and so on. Like this you can derive all these terms of Euler Cauchy equation. So third step is to substitute the values of x into dy by dx, x square into d square y by dx square, and so on in the Cauchy's homogeneous equation. If you substitute these terms in the Cauchy's homogeneous equation, the given equation reduces to a linear differential equation with constant coefficients in the variables y and z. Once the equation is a linear differential equation with constant coefficients, you know how to solve that equation. So we will be solving this linear differential equation with constant coefficients in the variables y and z. But we are given a non-homogeneous linear differential equation with variable coefficients in y and x. Now that variable coefficient equation is reduced to a linear differential equation with constant coefficients in the variables y and z. Because we know how to solve it, we will be solving it, but the solution will be in terms of y and z. But we require solution in terms of y and x. Our aim is to solve Euler Cauchy equation. It is in terms of y and x. So we have to write the solution also in terms of y and x. So in order to get the solution of the given differential equation in y and x, replace this z by log x to base e, which gives the complete solution of the given differential equation in the variables y and x. Problems on Euler Cauchy equation or Cauchy's homogeneous equation. Let us understand this method more clearly by solving some problems based on Cauchy's homogeneous equation. Solve x square into d square y by dx square plus x into dy by dx minus 4y is equal to x square. Now let us see how to solve this equation. First step is to write the given differential equation, that is x square into d square y by dx square plus x into dy by dx minus 4y is equal to x square. So now if you observe this equation, it is a non-homogeneous equation and it is a linear differential equation but with variable coefficients. It is not a constant coefficient linear differential equation. Then we observe this equation carefully. It is a Cauchy's homogeneous equation because it is of the form x square into d square y by dx square plus x into dy by dx minus 4y equal to x square. So identification of the differential equation is completed. You have identified that this is a Euler Cauchy equation. So your next step is to put x equal to e power z and x into dy by dx is equal to capital dy, x square into d square y by dx square as a capital D into d minus 1 operated on y. Then this differential equation becomes capital D into d minus 1 plus d minus 4 operated on y is equal to e power 2z. So this can be further simplified as d square minus 4 operated on y is equal to e power 2z. So this is of the form f of d operated on y is equal to some function of z. Here that function of z is e power 2z. In f of d, what is this d? This d is d by dz. So this is a linear differential equation with constant coefficients in the variables y and z. Here dependent variable is y and independent variable is z. So we have reduced a variable coefficient linear differential equation to a constant coefficient linear differential equation. This is a variable coefficient linear differential equation in the variables y and x, and this is a constant coefficient linear differential equation in the variables y and z. Therefore this is the symbolic form of the constant coefficient equation. So first next step is to find the auxiliary equation. The auxiliary equation is writing d is equal to m and equating d square minus 4 to 0, that is m square minus 4 equal to 0, which implies m is equal to plus or minus 2. Here roots are real and distinct, therefore complementary function is given by c1 e power 2z plus c2 e power minus 2z. So this is the complementary function for this linear differential equation with constant coefficient. So complementary function will be in terms of its independent variable. Here independent variable is z, so complementary function is in terms of z, but we require solution in terms of y and x. So complementary function should be in terms of the independent variable involved in the given differential equation. So what is the independent variable involved in the given differential equation? It is small x. So complementary function of the constant coefficient equation can be called as the complementary function of this Euler Cauchy equation only when you replace z by log x or e power z by x. So this becomes c1 into e power 2z can be written as e power z whole square, that is e power z is x, so x square plus c2 into e power minus 2z can be written as e power z whole power minus 2, so that is x power minus 2, that can be written as 1 by x square. So complementary function for the given non-homogeneous variable coefficient linear differential equation is c1x square plus c2 x square. Now we need to find particular integral of the constant coefficient equation in the variables y and z. So particular integral is 1 by f of d operated on function of z, and here function of z is e power 2z. So it comes under case 1. What is case 1? 1 by f of d operated on e power ax is case 1, but it is in terms of z. So we follow the procedure for finding particular integral in case 1, that is put d is equal to a if this denominator is not equal to 0. What happens if we substitute d is equal to 2? This denominator is going to become 0. So in that case we should not substitute 2 in place of d, because f of 2 is 0. So if f of 2 equal to 0, we have to differentiate this with respect to d, and we have to write z here. We have to multiply this with z, differentiate this f of d with respect to d, and then operate on e power 2z. So this will be z into 1 by 2d. 2d is the derivative of d square minus 4. So z into 1 by 2d operated on e power 2z. Now if you substitute d is equal to coefficient of z here, that is 2, we are not getting 0 in the denominator, so we substitute d is equal to 2 here, which gives z by 2 into 1 by d operated on e power 2x. What is 1 by d? 1 by d is nothing but integral. So 1 by d operated on a function of z will give you integral of that function into dz. So 1 by d is nothing but integral dz. So instead of 1 by d, you will be writing integral, write this function and integrate it with respect to z, which is equal to z by 2 into integration of e power 2z is e power 2z by 2. But the particular integral is in terms of z, because this is the particular integral for the constant coefficient linear differential equation, which is in the variables y and z. We require the particular integral in terms of x. So replace z by log x or e power z with x. With this substitution, this particular integral will become e power 2z is e power z whole square, e power z is x, so x square, and z is log x, so x square into log x by 4. This is the particular integral of the given Cauchy's homogeneous equation. What we have done here in complementary function and in particular integral, we have replaced z with log x or x with e power z. Therefore, the complete solution of the given equation is y is equal to complementary function plus particular integral. That is, y is equal to c1 into x square plus c2 by x square. This is the complementary function plus this is the particular integral, x square into log x by 4. Let us do one more problem based on this model. Solve x square into d square y by dx square minus x into dy by dx minus 3y is equal to x square into log x. Solution. Your first step is to identify whether we are given the Cauchy's homogeneous linear differential equation or not. Let us identify this one, whether it is a Cauchy's homogeneous equation or not. It is a linear equation because the degree of the dependent variable and its derivatives is 1. It doesn't contain any products of dependent variable and its derivatives or products of various order derivatives in this equation. So it is a linear equation. And look at RHS. It is a function of x. So it is a non-homogeneous linear differential equation. But this is not a constant coefficient equation because coefficients of dy by dx and d square y by dx square are not constant. So it's a variable coefficient equation, and specifically it takes the form of a Cauchy's homogeneous linear equation. That is x square into d square y by dx square minus x into dy by dx minus 3y is equal to x square log x. So it is a Cauchy's homogeneous linear equation. So identification of the differential equation was completed. Now we need to solve it. This equation can be solved by reducing it to a constant coefficient linear differential equation. For that, put x is equal to e power z, that is z is equal to log x, so that x into dy by dx can be written as capital dy, x square into d square y by dx square can be written as d into d minus y operated on y, where capital D is d by dz. Now substitute these values in the given Cauchy's homogeneous equation. Then Cauchy's homogeneous equation reduces to, say instead of first term we can write d into d minus 1 minus d minus 3 operated on y is equal to this x square is e power 2 z, because x is e power z, x square is e power z whole square, which is e power 2 z, into log x. Log x can be written as z. So finally RHS is z into e power 2z. So this equation can be further simplified as d square minus 2d minus 3 operated on y is equal to z into e power 2z, which is a linear differential equation with constant coefficients in the variables y and z. Here y is the dependent variable and z is the independent variable. So we apply the procedure for solving this non-homogeneous linear differential equation with variable coefficients for this equation. So your next step is to find the auxiliary equation. So auxiliary equation is obtained by replacing d by m and equating f of t to 0. So you need to equate d square minus 2d minus 3 to 0 by replacing d by m. So auxiliary equation is m square minus 2m minus 3 is equal to 0, which can be further simplified as m minus 3 into m plus 1 is equal to 0, where m is 3 comma minus 3. 3 and minus 3 are the roots of the auxiliary equation. If we observe the roots are real and distinct. Therefore, complementary function is given by c1 e power 3z plus c2 e power minus z, because complementary function should be in terms of independent variable. We are solving a linear differential equation with constant coefficients in the variables y and z, with z as independent variable and y as dependent variable. So complementary function will be in terms of the independent variable involved. So complementary function will be in terms of z, but our differential equation is in terms of y and x, where x is the independent variable. So we need complementary function also in terms of the independent variable x, and that can be done by simply replacing e power z by x here. So it will be c1 into e power 3z can be written as x cube plus e power minus z can be written as 1 by z. Therefore, complementary function for the given Cauchy's homogeneous equation is c1 x cube plus c2 x. Now we need to find particular integral. Particular integral is given by 1 by f of t operated on a function of z here, because Our linear differential equation with constant coefficients is in terms of y and z with z as independent variable. So particular integral will be 1 by some function of d operated on RHS of the non-homogeneous linear differential equation with constant coefficients. So this is the right hand side of the non-homogeneous linear differential equation with constant coefficients. So we have to operate 1 by f of d on e power 2z into z. And if you observe it carefully, it comes under case 4. This particular integral can be evaluated by using case 4. What is case 4? 1 by f of d operated on e power ax into v, where v is any function of x. So it is e power ax into 1 by f of d plus a operated on v. So if you observe this carefully, it is of the form e power 2z into z. So instead of x, we are having z here, because d is d by dz. Therefore, it takes the form of case 4, which is equal to e power 2z into 1 by f of d plus 2 operated on this z. So wherever you are having d, we need to write d plus 2. Here 1 by f of d operated on e power ax into v is equal to e power ax into 1 by f of d plus coefficient of x in e power ax operated on v. This is what we are doing here. So this can be written as e power 2z into 1 by f of d plus 2, that is d plus 2 whole square minus 2 into d plus 2 minus 3 operated on z, which is equal to e power 2z into 1 by d square plus 2d minus 3 operated on z. If we simplify this denominator, we will get this as d square plus 2d minus 3. Now we observe that the particular integral takes the form e power 2z by 1 by d square plus 2d minus 3 operated on z. So we observe this carefully. It is nothing but 1 by some function of d operated on z. Therefore, this comes under case 3. How will you evaluate particular integral in case 3? By treating 1 by f of d as f of d whole power minus 1 and expanding f of d whole power minus 1 using binomial theorem and operate each term on z. This is what we have to apply here. So this is equal to e power 2z into 1 by, we'll further simplify this denominator so that binomial expansion is possible. So this can be written as e power 2z into 1 by minus 3 into 1 minus 2d by 3 minus d square by 3. See, we have taken minus 3 common from the denominator so that it takes the form of 1 minus some function of d. So this is equal to minus 1 by 3 into e power 2z into 1 minus 2d by 3 plus d square by 3 whole power minus 1 operated on z. So now we need to expand it. We use the expansion of 1 minus x whole power minus 1, that is 1 plus x square plus and so on. But instead of x, we are having 2d by 3 plus d square by 3. So 1 minus 2d by 3 plus d square by 3 whole power minus 1 can be expanded as 1 plus 2d by 3 plus d square by 3 plus and so on operated on z. So this can be written as minus 1 by 3 into e power 2z whole into 1 plus 2d by 3 plus d square by 3 plus and so on operated on z. Now operate each term of this expansion on z. We get minus 1 by 3 into e power 2z whole into 1 operated on z is z plus 2 by 3 into d operated on z is 2 by 3 plus d square by 3 operated on z is 1 by 3 into 0, double derivative of z is 0. From next term onwards, all the remaining terms contains minimum term as d square. Therefore, all the higher powers other than 1 when operated on z will become 0. So from this expansion, when operated on z, we get only z plus 2 by 3. So particular integral is minus 1 by 3 into e power 2z into z plus 2 by 3. So this is the particular integral of the given non-homogeneous linear differential equation with constant coefficients in the variables y and z. But we require the particular integral in terms of x. For that, we will be replacing e power z by x or z by log x, which gives minus 1 by 3 into e power 2z can be written as e power z whole square, that is x square, into z is replaced by log x, so log x plus 2 by 3. This is the particular integral of the given Cauchy's homogeneous equation. Therefore, complete solution of the Cauchy's homogeneous equation is y is equal to complementary function plus particular integral. Now, if you observe this carefully, it is a relation between the dependent variable and independent variables which satisfies the given equation and which contains two arbitrary constants. Therefore, we call it as the complete solution. So, in this problem, what we have done, we are given a Cauchy's homogeneous equation, which is a variable coefficient equation in the variables. In this problem, we are given Cauchy's homogeneous equation, which is a variable coefficient linear differential equation in the variables y and x. We have reduced this equation to a constant coefficient linear differential equation in the variables y and z, and we have solved that constant coefficient linear differential equation by finding a complementary function and particular integral, and we have replaced e power z by x or z by log x. Finally, we got complete solution of the given linear differential equation with variable coefficients in terms of y and x. Thank you.